Hey guys, welcome back to my channel, and today we're going to be talking about applications of linear algebra in science. So first, one application of linear systems in science would be when we want to balance chemical equations. So for example, here we have an equation that represents boron sulfide reacting with water to form boric acid and hydrogen sulfide gas. So to balance this chemical equation, we're going to need to find whole numbers that are the coefficients of these compounds. So like x1, x2, x3, and x4. And they must ensure that the total number of atoms of each element on the left will equal the total number of atoms of each element on the right. So in this case, all the boron atoms would have to equal the number of boron atoms on the other side. The same goes for sulfur, hydrogen, and oxygen. So we can set up a vector equation that will describe the number of atoms of each type in this reaction. And because this reaction involves boron, sulfur, hydrogen, and oxygen, our vector will have 4 entries. So we can just have our vector be like this. So it'll be C1, C2, C3, C4. And again, the first entry will be boron, then the second will be sulfur, the third will be hydrogen, and the fourth will be oxygen. So for this first compound, its vector would be 2 boron, so 2, and then 3 sulfur, so 3. And then it doesn't have hydrogen and oxygen, so the third and fourth entries are 0. And the same goes for this second compound. So it has 0 boron, 0 sulfur atoms, 2 hydrogen atoms, and 1 oxygen atom. And then this third compound has 1 boron atom, 0 sulfur atoms, 3 hydrogen atoms, and 3 oxygen atoms. And then this fourth compound has 0 boron atoms, 1 sulfur atom, 2 hydrogen atoms, and 0 oxygen atoms. So now to balance this equation, we're going to create a vector equation that represents this reaction. So we have x1 times our vectors plus x2 times our vector, and then it will equal x3 times 1, 0, 3, 3 plus x4 times 0, 1, 2, 0. And then now if we move all the terms to the left side, this will simplify it so that we can row reduce it later. So we'll do x1, 2, 3, 0, 0 plus x2, 0, 0, 2, 1, and then minus x3, 1, 0, 3, 3, minus x4, 0, 1, 2, 0, will equal 0. So now we can write this into an augmented matrix and make sure that the third and fourth vectors are negated because of the negatives in front of them. So negative 1, 0, negative 3, negative 3, 0, negative 1, negative 2, 0. And now all we have to do is solve for this matrix. So what I'm going to do is first make every row have a leading 1, so it's a bit easier. And now we're going to do negative row 1 plus row 2. So negative 1 plus 1 is 0. Negative 1 half. Negative negative 1 half plus 0 is 1 half. And then the 0 doesn't do anything. And then same for row 4. I'm going to do negative row 3 plus row 4. So negative 1 plus 1 is 0. Negative negative 3 halves. So positive 3 halves minus 3 is negative 3 halves. And negative negative 1 is just positive 1. Now I'm going to add the fourth row to the third row. I'm going to do negative row 4 plus row 3. So we get negative negative 3 halves, which is positive 3 halves, plus negative 3 halves, which is 0. Negative 1 minus 1, which is negative 2. And then here I'm just switching the order of the rows. And now we're going to do 3 times row 3 plus row 4, so we can create a 0 row in the fourth row. So now I'm going to do row 1 plus row 3. And I'm going to divide row 3 by 1 half. So now our matrix is in reduced row echelon form, and we have our general solution. So x1 minus 1/3 x4 equals 0. x2 minus 2x4 equals 0. x3 minus 2/3 x4 equals 0. And x4 is free. So x1 equals 1/3 x4. x2 equals 2x4, and x3 equals 2/3 x4. So x equals 1/3 x4, 2x4, 2/3 x4, and x4. And this is just x4 times the vector 1/3, 2, 2/3, and 1. So if we let x4 equal 3, we'll have 3 times 1/3, 2, 2/3, and 1, which gives us 1, 6, 2, 3. So now we can plug those into our coefficients x2, x1, x3, and x4. And we get B2S3 because the coefficient is 1, and then plus 6 H2O yields 2H3BO3 plus 3H2S. So yeah, that's how we balance a chemical equation using linear systems. So we can also apply coordinate systems from linear algebra into crystallography. So by coordinate systems, we basically refer to the unique representation theorem. So if this is the basis for a vector space V, then we know that for each x and v, we can write x like x equals C1, B1, and then all the way to Cn, Bn, where C1 and then Cn, all of those are a unique set of scalars. And once we know that, we can say that the coordinates of x relative to our basis, so relative to the basis B, and they're also called the B coordinates of x, and they're just the weights 1 all the way through Cn, such that x equals C1 B1 plus all the way to Cn Bn. So basically, we can write a vector relative to a basis like this. So in crystallography, we can describe a crystal lattice by choosing a basis with vectors for R3. And these 3 vectors correspond to the 3 adjacent edges of one unit cell of the crystal. And then to make the entire lattice in crystallography, we just stack together many copies of this one cell. And one example of a unit cell is like a simple monoclinic cell. And this would be U, V, and W. And this is just kind of what it would look like. And then in crystallography, to find the coordinates of those atoms that are within the crystal, we just give the coordinates relative to the basis, which is why coordinate systems are useful. So instead of being in terms of like your typical unit vectors, I would write coordinates for those atoms in terms of the vectors U, V, and W. So now we have an example about the crystal lattice for titanium. So it has a hexagonal structure. And though these 3 vectors here, 2.6, negative 1.50, 0.30, and 0.04.8, in R3 form a basis for this unit cell. Here's a picture of the crystal lattice for titanium. The numbers in the vectors are angstrom units, and 1 angstrom unit is 10 to the power of negative 8 centimeters. So now if we're given that one of the octahedral sites is 1/2, 1/4, 1/6 relative to the lattice basis, we can use linear algebra to find the coordinates of the site relative to the standard basis in R3. So all we have to do is take note of these 3 vectors, and because this is already relative to the lattice basis, we know that these are just the weights. So 1/2 is the weight that corresponds to this first vector, and then 1/4 is the weight that corresponds to the second vector, which is 0.30. And then 1/6 is the vector that 0.04.8. So now all we have to do is multiply them together, and we get 1.30 and 0.8. Again, this is just the coordinate vector relative to this basis. And then we already know the basis, where these are the 3 vectors in the basis. And all we have to do is multiply those vectors by the weights, and then we got this. Example would be this. So if we're given that one of the tetrahedral sites is 1/2, 1/2, and 1/3, and we want to find the coordinates of the site relative to the standard basis of r cubed, we would do the exact same thing because we already know the vectors of the basis. So this is telling us that the coordinate vector is this. So again, to find the vector relative to the standard basis, we would just do this. PB is just all those three vectors again. So we can also just write it this way instead of the way we did it above. But it is the same thing, 1/2, 1/2, 1/3. And then we would just do row column multiplication, which is what we wrote up here. This would give us 1.3, 0.75, 1.6. So last up, eigenvectors and eigenvalues also have applications in medicine, such as in virology. So first we're going to start by reviewing what eigenvectors and eigenvalues are. So an eigenvector is basically a non-zero vector x such that ax will equal lambda x for some scalar lambda, and A is an n by n matrix. And then we also know that a scalar, this lambda, will be an eigenvalue of A only if there is a non-trivial solution x to this equation. And this is because x cannot be the trivial solution, or else our eigenvector will be the zero vector, which doesn't make sense because you can't really scale the zero vector. So that's why we need a non-trivial solution to this equation. So in this one study about eigenvalue analysis and COVID-19 patients, eigenvalue analysis that came with fixed eigenvalues and eigenvectors was performed. In this study, it was found that 2D analysis was sufficient to demonstrate how the viral infections of COVID patients are instability-induced phenomena, and their dynamics were able to be determined by eigenvalues and eigenvectors. So basically, if we have a 2D space and we have a vector such as vector u, now that if u is an eigenvector of a matrix A, which is n by n, multiplying by A will scale it somehow, so we can just pretend it scales it by 3. So we get 3u. And this also tells us that the eigenvalue would be 3. So relating to this study again, so this study showed that when the sign of the eigenvalue switched, so it changed from positive to negative, it indicated a transition from the stage where virus load increases in patients to the stage where viral load decreases. And the sign switching of the eigenvalues indicated how COVID-19 epidemics enter subsiding stages. So basically, this meant that the number of daily new COVID infections decreased from day to day. Oh yeah, that's just an application of eigenvalues and eigenvectors to medicine. Now we can review how to just solve for basic eigenvalues. So when you have a matrix and you want to find its eigenvalues, for example, if we have the matrix 5, 3, 3, 5, to find the eigenvalues, we have to set the determinant of A minus lambda times the identity matrix equal to 0. So A minus lambda I in this case would just be 5 minus lambda, 3, 3, and 5 minus lambda. And the determinant of this would just be AD minus BC, so 5 minus lambda squared minus 3 times 3, which is 9, and we can set it equal to 0. And then we can just factor it out. We can factor this into lambda minus 8 and lambda minus 2. So we know that the eigenvalues are 2 and 8. This equation here is just the characteristic equation, and a scalar lambda will be an eigenvalue of the n by n matrix A if and only if that scalar lambda satisfies this characteristic equation. So yeah, that's about it for today's video about applications of linear algebra in science. And yeah, thanks for watching.